Hello and welcome back. At the moment I've got my Siva Eratosthenes code loaded up, which will output prime numbers in the 16-bit range on the LCD here. I'm still really proud of this piece of code actually, because it was one of my early big stress tests of the ALU and the whole kind of processor, and it's really quite efficient. But you can kind of get the impression looking at this that this is going to take a while. Now I want to show you something. I'm going to switch it from trace mode into run mode and then back. The kind of screen glitched around for a little bit and now it started outputting the numbers again, but it's obviously moved on a very long way in the sequence. The system's currently clocked in run mode at the moment at 1 MHz. We can go higher than that, but that's plenty fast enough at the moment. And obviously the LCD cannot keep up. Now I've always said this was going to be a temporary display, but I think we're kind of hitting a point where it would be better if this worked well, as opposed to the hacky way I put together in the first place. To be honest, I should have done it properly right at the beginning, but I thought I wasn't going to have it for that long. So on the LCD module, you've got the ability to read and write a control address and a data address. And I only implemented the ability to write to each of those because you use the control address to kind of clear it and change other configuration options and use the data to actually write text out. So what I want to do today is implement the read back from those addresses. So we need a more complicated circuit to interface it back to the CPU. One of the side effects of that is that I will then be able to read the busy flag so we can stick the code into a wait loop when it's clearing the screen or moving the cursor around, and we can actually get the display to update as fast as possible, because right now if I clock it too high it all just goes wrong. Okay, so this is the circuit we designed and built in part 55, which is where I was referring to it as a temporary display. I'm still regarding it as temporary, but it would just be good to have it work a bit better. So these are two of the control lines going into the LCD module, which are register select and the enable line. And they work differently from the load data and load command lines coming out of the CPU. And so we had to build this simple circuit to translate between them. But the LCD module actually has an additional line of interest. It's got this read-write line. Now when it's low it means it's writing, and so these lines operate like this. On the breadboard at the moment we've just got the read-write line held low. But if it's high, these are actually asserting bits of data back. Now the crucial thing to note here is when the read line is high and the enable line is high, this is going to be pushing data out of the 8 data lines, which at the moment we've got connected directly to the main bus. So we want to be careful about that. We only want to be doing that at the exact time when we know nothing else is asserting to the bus. So we need more than these 2 lines from the CPU, and our I/O ports are divided up just like on the registers where we've got load lines and assert lines, and we're using 2 pairs. So in this case, when we're loading, it looks just as before, and the assert data and assert command lines stay high because they're active low. And then during an assert operation, the load lines stay high and the assert lines fall low. At the moment in this circuit, we are ignoring both of those assert lines and we're not generating the read-write line. Okay, so let's add the extra input lines and the extra output. So it's not quite so clear now where these have to connect up. Let's have a think about this. We've got the set reset latch here that's implementing the register select line. And previously, if we did a load data, it would set, and if we did a load register, it would reset. And then we just use the appropriate output from there to control this. Whereas now we want to switch the mode to data or set the mode to register if either one of these goes low. So our logical operation here is if load data or assert data activate this side of the set reset latch. Of course, these are active low connections. So what we're actually interested in doing is having an AND operation, because then the output will go low if either of these go low. And the same applies for the register side. Okay, so that's our register select line being generated. Now our enable line, we were previously NANDing together the load data and load register line, but we're going to need to do something with all 4 lines now. But just the same as for the set reset latch, this represents either of the data operations and this represents either of the register operations, we can apply the same here to the enable output. Now lastly, we just need to think about this read-write line. So we can look back over here and we can pay attention to the fact that the read-write line goes high if either the assert data or the assert command lines go low. And that's actually quite a simple operation. So once again, this is just going to be a single NAND gate on the two asserts. So I quite like this. Even though these signals look very, very different, we were able to extend our basic circuit and produce a workable translation between the 4 lines of the CPU build and the 3 lines of input to this module. And we've used the one remaining NAND gate on the NAND chip we've currently got in that LCD module, and we do need to add a chip with AND gates on it. Okay, so let's have a crack at building that. Okay, so let's pull this out of here. We've only got one of these modules though, so we need to keep that. Got a fresh new breadboard, but I think we can fit it all on here. Now, to give us a bit of extra room, what I think I should do is place this down like that, and then we've got the extra space up here to do some work. Okay, so initially we got the power and ground lines up here. Stick them straight in like that. Then we've got the intensity control. Now the data sheet says this needs about 0.5 volt, but we stick a potentiometer on there to create the contrast setting. So if I bring that to the top half of the PCB, this should do the trick. Okay, that's already much more compact. Okay, so 4th line along, that's the register select. So we're going to need to build that. So pin 5 here, and we've tied that low on the previous breadboard. So that is the read-write line. So I think for now I'm just going to pull that low, but we're going to want to come back to that. And the 6th line here is enable. Okay, we're going to need to start building the circuit. Okay, so this is 74LS00, which is 4 NAND gates. This batch are annoying because it's very difficult to read the number. And this is 74LS08, which is 4 AND gates. Now previously I did the set reset latch across, but because of the way the inputs line up here, I think it would be good if we used just the top pair for the set reset latch and then the top pair for the inputs here, because then we can keep all the signals on one side, at least for the register select line, and that I think will be a bit neater. So firstly, let's take the output of this NAND gate, tie it to the second input of this one, and the output of this one and tie it to the second input of the right hand one. Okay, so then I'm going to take the output from this AND gate and pass it into this previously unconnected input here. And the same for the second NAND gate from the second AND gate. So these 4 lines here need to be our inputs. Okay, I've made up a fresh new cable for this. Rather than separating it out like I did before, I've put that all on one header, because what I want to do is convert this to a PCB and then use the same pin ordering. So I've got power on this header, so let's grab that. Now the next 4 lines are in a row, but we've got to have one bit of space here for the output. So that's the load and assert for the control register. And then we need the load and assert for data. Okay, so that should be register select being correctly produced now. I think I want to get some LEDs in for this stuff. So these are the outputs from the set reset latch. I just need the one of those for register select, but yeah, I need to bring that wire across better. Okay, so now we need to generate the enable line. Now previously we did that just by NANDing together the load lines, but now we want to NAND together the outputs from the two AND gates. Okay, so that green line there, it's going to be easier to take it on the right, and the second green line, be easier to take that on the left. There's our enable line. Now we need that read-write select. So for that, we need to NAND together the two assert lines. First one, the second. Okay, so the next 8 points along here are the data lines, and then we probably want the backlight power. Right, these are messy. It is not possible to make wires stay straight over this length. Or at least I can't straighten the wire out in the first place after taking it off the reel. I'll worry about those ones later. That's pretty neat. Okay, so if we've done this right and we've designed the circuit right, this should implement the new functionality, but without anything happening on the assert lines, it should operate as before. Let's give that a test. Got LEDs on the register select, but let's put them on read write and enable. Okay, didn't plan these placements well enough. Well, that's not very promising, is it? Okay, it's not switching between data and commands, so I'm guessing I've messed up something there. Okay, so that first little flurry should be command and then data. The enable line seems to be changing correctly. The read-write line is low, which is what we want. I do need to get a new pogo pin for this because I broke it the other day. This feels correct. Oh, hang on. That's a floating line, and it shouldn't be. So that line is seeing the variation we expect, and that pin isn't. This doesn't have a breadboard issue. So that's getting the signal. Let's just try bending these pins slightly. Okay, it's missing every other line. Is that just because we missed this startup? Yeah, I think we just missed the initial startup then. Okay, so this appears to be working correctly, but of course it's essentially doing exactly the same as the previous circuit because we haven't done anything with the assert lines for getting data back from the module to the CPU. We're going to need to write some code for that. Okay, so first thing is we actually need to be able to get at the control register for a read. We're getting very low on unused instruction encodings. Just about everything is here now though. Okay, here's our new instruction. So we're just saying that that instruction is implemented by telling LCD command to assert, which is what's going to lower that command assert line. I think I was calling it control when building the circuit, and then load into register A. Just need to declare that as being on IO port 14. So I added these NOPs into the breakpoint instruction encoding just to keep the pipeline clear while I was trying to debug some stuff, and that works fine for the assembler, but my code that generates this pipeline header file expects to see the instruction in the first couple of bytes. Right, so ROM 2A has changed. So now we need to look back at this primes code. I think I do everything with the display library. Okay, I'm not using the hex routines at the moment, but I will need to patch them later. Busy bit is in the top bit of LCD command, so I should be able to get it into the logical carry flag with a shift left. Oh, actually, let's ignore that for now. It's annoying actually, this loop's going to get a bit slower. Okay, so I haven't updated the initialization function, but we can run that in trace mode. Right, let's give it a go. So our string output should be a bit slower. Our initialize function hasn't been updated yet. Okay, well that doesn't look right. What happens if we run? Ah, now you see, I can see the text looking okay here, although things are misaligned horizontally, but this looks like the correct text is coming out, and that's going to complete any second now. That's the correct last prime, and the text isn't mangled. What's going on there? Right, only thing we're really doing different here is the read line. So let's take a look at that. Let's have a look at the enable line. You see, at that level, it looks correct. If I run it at high speed mode and zoom in, it looks okay. But the only thing I'm worried about is the fact that the enable line lags that read line a little bit. It's really the falling edge we want to worry about, but that's going to be the same offset. Okay, so let's take a look at this. Right, so read-write line goes high, which we're seeing. It's got the enable line going high after that. TAS is 0, so the fact that they're going high at the same time shouldn't matter. In fact, at the moment the enable line is definitely going high very slightly later than RW. Here's the problem. Our enable line actually drops slightly after the read-write line. The spec is saying it wants it there for 10 nanoseconds. Okay, this bit of timing might actually be difficult to do. But if you think about what we've got at the moment is the read-write line changes and then the enable line changes. So for a tiny fraction of the operation, the lines are actually configured as if we want to do a load operation instead of an assert operation. And that's because this NAND gate responds to the control lines quicker than this one. Now we've got 2 spare AND gates, so we could actually put AND gates on these 2 lines as a dummy and basically slow this operation down so it happens at the same time as this one. It's the same. Okay, let's put that back. I've got a different idea. So instead of trying to extend the read-write line, maybe we can shorten the enable line. On the load operation, the enable line is half a cycle, but because our assert lines go for the full cycle, that's what's causing the problem. So how about we AND that enable line with the clock? Fortunately, I've just freed up a clock line there. That looks promising. Let's restart. Didn't do the line selection properly. Clear was correct. Maybe we just got the code wrong. Ah, no, look at that. Let's load that into B. Okay, that's good because that's an explanation for why that's not working. Now we need to do this initialization correctly. The wait needs to happen before we access the register. This would probably be better with a little sub-function, but I'll just copy-paste it for now. Oh, actually, there is something else I wanted to do. It's always bugged me, but that has no space. It's also bugged me that it never tells us 2 is prime. Because I've got an optimization to avoid all the even numbers. If I just stick that at the start as a string, it will start looking right. Ah, I even thought about it before. This is good. Yeah, it's working. Let's see what happens if we switch it up to top speed. Okay, I'm seeing the structure correct. It's not jumping around at all. So that's 30,000, 40, 50. Okay, excellent. These are the correct numbers. Okay, this is the fastest we've seen the prime number program complete, because this is much faster than the UART was. Ah, this is great. So without displaying anything, this used to take about 6 seconds. What's that, about 9? Okay, so that's still waiting for the LCD a little bit, but it's far, far quicker than the UART was, if I remember correctly. I may need to write some code soon that stresses the processor a bit more. Okay, it's a shame I got that wrong. I've had to introduce the clock line, but fortunately we actually had a spare output for the clock line nice and close. Wonder if we might come across a need for the clock line in more places. I should have put more outputs for it down the side. Okay, so I am really chuffed with this. It's awesome to see the processor running that quickly. Sometimes I really enjoy just watching it at trace speed, but I am really pleased with this progress. It's going to be nice to have this circuit being able to run a bit quicker, because I want to finish off the ALU conversion to PCB. I've got some changes I'm working on memory, and then we're on to some interesting stuff. Okay, hope you found this interesting. Thanks a lot for watching. I'll see you again soon. Goodbye.